Good morning. All right. So today we're going to kind of wrap up our discussion on lines. We're going to put everything together about linear equations. We're exactly where we would have been if we were in class, if you're watching these things live. I have on Pearson all the homework and all the exams except the final exams. Sorry, the linear equation exam posted. I want to release those all tonight, and that way you can take them when you want. We only have one section of material to do after lines, which is exponents in equations, but it is a chunk of material. So we'll start that on Thursday. But today's going to be fairly casual. I'm going to do examples of all the word problems that relate with lines, and build out from there. Or not build out from there, kind of to leave it at there. So it's going to be a bunch of examples of how linear equations fall into applications. And all of the material that will walk us through the end of the course will be on Pearson tonight. I will get my email out, which I didn't do last week. I tended to talk to everyone in here or responded to other people's emails. I also have a couple emails that I've been getting off the homework that I'll put some examples up on the YouTubes. All right, so I'm going to kind of just summarize what we have with lines, from the most general form to what helps us. So in general, an equation of a line, that blue, let's make that a little wider. In general, an equation of a line is some constant times x plus some constant times y equals another constant. But we have these two variables. And so this is the general equation of a line. If we get something in the general form of the equation, that's fine, Tina. That's fine. You do what you need to do. I will keep you in mind. Be well. If we have this form of the equation, it has all the information needed for a line. The things to note are the power of x is 1 and the power of y is 1. Now, the form we tend to prefer is y equals mx plus b, where m is the slope. And the slope is the part that describes how steep a line is. And we write it as how the equation is changing in the y direction divided by how it's changing in the x direction. Or the difference in 2 point values in y and in x. And if we want to think of words, it's how it's rising over how it's running. Now, the yellow equation we did here, we can convert into our slope-intercept form. And slope-intercept form helps us. Oh, yeah, I have to actually say what the intercept is. Sorry. Let me do that first, and then we'll do the conversion. Get back to my red here. And B is the y-intercept. It is the y value when x is equal to 0. It is where crosses the y-axis. Now we have what we can do here. So I'm going to scroll up. We started with the general form of the line ax plus by equals c. Gave an example here. I said the form we like is y equals mx plus b, because we can see things here. We can see this m and we can see this b. So let's look at the line we have. Let's look at this 3x plus 6y equals 9 and convert it. So 3x plus 6y equals 9. The thing I want to focus on is that we want the y and the y only on the left-hand side, or on its own side, right? We want to isolate y on its own. So in this case, I have y over here, but x is in the way. Let me give some more room now that I have this repeated. There we go. So I'm going to subtract 3x from both sides. That will cancel here, leaving me with 6y equals, but we write our x first, like that. And now I'm going to divide everything by 6. To get y all on its own. That should be enough. So I get y equals negative 1/2 plus, what, 3 goes into each 3/2. And there's my equation of the line. Now why I like this, every pun intended, I'll scroll down a little bit more, is I can see clearly, now the rain is gonna, sorry, bad musical puns, that hanging out in front of my x is my m, and there is my b. So this has an m, or a slope, of negative 1/2. It goes down 1 for every 2 it goes forward, or it goes up 1 for every 2 it goes backwards. And it intercepts the y-axis at 3/2. So if I draw a little axis here, and I come up 1.5, there's 3/2, and I go down 1 over 2, about like that. That's my line. And so this is why we prefer this form, y equals mx plus b. We see information in this form that lets us quickly draw the line if we need to draw it, or even if we want to talk about it. By looking at m, we know that it is a decreasing function because it has this negative sign. Because it's 1/2, it's a shallow decreasing versus a steep decreasing. The bigger the number, the steeper the line. If it's negative, it's decreasing. If it's positive, it's increasing. And this intercept tells me the starting point, right? That's y equals 3/2, or that's the intercept right here. And so this form of a line, it helps us see what's happening. If we start evaluating the slope as the rate of change, this form also tells me if I input some value in x and multiply it by the rate of change, I get an output of some value. And that's the thing we're going to try to focus on the most here today, is the idea of the slope being a rate of change, and using that in different situations to take equations and having an equation we can already put them into. And so this format of y equals mx plus b helps us. Y equals mx plus b. And the other thing we learned about a line in our summary of the things we know about a line is if I have 2 points I can find the slope using m equals the difference in the y values between the 2 points divided by the difference in the x values between the 2 points. And once I know the slope, I can find the equation of the line. If I use this form, which is called the point slope form. And so we're going to look at the point slope form in a couple examples. The thing to note is 2 points is the same as having 2 pieces of data. And I'm going to use the 2 pieces of data example to use the point slope equation and to use it to show how we would actually solve a word problem with that. And I'm going to think in temperature. A lot of us have this thing we have to memorize how to convert from Fahrenheit to Celsius or Celsius to Fahrenheit. And we're going to do both. And we're going to do that using a line. So I'm going to come down here and start a graph. And so the thing we're going to use is this point slope form with 2 pieces of data. And so in my notes here, I'm going to say temperature conversion. As a line using 2 pieces of data. Alright, so let's draw a place to put our lines. Let's draw our our points of data. And what I'm going to do here is I'm going to let everything I know about lines help me here. So we're going to say I want my answer to be in Fahrenheit. So instead of calling this y, I'm going to call it Fahrenheit. And my input is going to be in Celsius. So instead of calling that x, I'm going to call that Celsius. So I'm going to use the idea that y equals mx plus b, but it's going to be f equals some slope times Celsius plus b. So we're going to borrow the idea of lines, but what are the 2 points of data we have? Well, the 2 points of data we have for this temperature scale is from water. Water freezes. Now notice my points here. My points, my data pair, has to be C, F. And so water freezes at 0 Celsius, which is 32 Fahrenheit. And water boils 200 Celsius or 212 Fahrenheit. Notice that these pair of values can act like points. In fact, when Celsius is 0, F is 32. So my B equals 32. So my slope is my difference in y values, 212 minus 32 over 100 minus 0, which is 180 over 100, or 9/5. All right, divide that by 20, you get 9. Divide that by 20, you get 5. So I can put together, using this format, Fahrenheit equals 9/5 Celsius plus 32. And we get the conversion from one temperature to another. Notice the thing we did isn't a line in space. All right, I don't lay out Celsius and Fahrenheit as places within space, but I used an assumption that the data is linear, that the rate of change in one determines the value of the other, and using the linear nature of this, I needed 2 data points. The data points I had was when water freezes and water boils. And we're able to build a temperature conversion using the ideas we have of a line. And that's the power of putting our variables onto a line, is we get this. Let's see, I rise 9 over 5. So this is a slightly steeper curve. And I can have a temperature line that I can plug any value in for C, and I get my value out in Fahrenheit. But we built that conversion using what we know about lines. And that's why we study lines. That's why we study graphs. And I can get from this that, well, Fahrenheit is a little bit higher in temperature than Celsius on the scale. It has a steep conversion curve, 9/5. It's not 1-to-1. So every degree I go up in Celsius, I go not quite 2 degrees up in Fahrenheit. Right? There's some things we can see visually from the graph, and we can pull apart from its rate of change and its intercept. And so that's why we study lines. We're not studying lines because we want all of you to go out and become geometers or surveyors and start breaking apart land into quad graphs and figure out, what's the rate of change in the east direction versus the northward direction. This isn't to make things work in geometry. It's to translate these ideas in English into a geometric term so we can get all of these ideas that we have in space back over to it. All right, let's look at some more of these. This is what I'm going to do today, is focus on taking these things that aren't lines, but using the mathematical nature of lines to help us solve some problems. Let's do this backwards. And the backwards one is not as pretty, but we'll get there. And that's going to be, so we want to convert from Fahrenheit to Celsius. And we're going to do the same thing. We're going to set a set of axes out. But now this is going to be my Fahrenheit values. And this is going to be my Celsius values. Which means my points I now list as Fahrenheit, comma Celsius. Well, what points do we have again? Water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. And water boils at 212 degrees Fahrenheit or 100 Celsius. Notice we don't have a y-intercept. This does not have a y-intercept, so we're going to have to use our, I'll put this over here in red. Y minus y1 equals m times x minus x1, except this is going to be c minus c1 equals m f minus f1. Right? We're using different names for our variables, but we're using the idea that they're linear to help us find an equation. So when we need to use the slope-intercept form, or the point-slope form, sorry, we have a point, which is the ones, and we have the slope. We have our variables. We need to find the slope first. So m equals my difference in y's over my difference in x's, or y2 minus y1 over x2 minus x1. And let's see, y2 is 100 minus 0 over 212 minus 32, which is 100 over 180, or 5/9. Notice, and this is something you should notice when you work on relationships of things, this is the inverse of what we did before, right? We're going the opposite way. In the previous one, we put in Celsius and we got out Fahrenheit. Now we're putting in Fahrenheit and we get out Celsius. Notice the rate of change, the 5/9, is the fraction we had before flipped upside down, right? Here we had 9/5. Here we had 5/9. That's something just to keep in mind because it does have meaning here. All right, so we're going to have C minus, well, for C1, I'm going to use 0, right? Because that's a nice 0. So we're going to use this as C1. Because again, I could use either. I could do 100 and 212. I'm trying to make the maths a little bit easier for me. So I'm going to use the 0 here. And then so we have 5/9 my Fahrenheit minus x1, 32. And this is usually how you see this conversion, because 5/9 times 32 doesn't come out nicely, and so people leave it like this so that they can calculate the conversion between Celsius and Fahrenheit. I am really going to stress here the importance that none of this has anything to do with moving through space, moving on a graph, moving on a grid. It has nothing to do directly with the physical object of triangles or geometry. What we have done is we have borrowed the ideas from geometry. We have borrowed the ideas of how things move through space, and we have let them represent points of data. The points of data we have decided to use are temperatures, and that lets us build equations. That's why we spent, about a week and a half now, playing with lines, because we're able to borrow this. And what we borrow when we do this is the idea that things move through space. And as they move through space, they rise or fall. There's everything we do is we have to move to get through space. We'll say that's 32, 0. And we go up 5 and over 9. So up 5 over 9 is like that. 9. Wanted to put this up here, and I'm kind of slowing my talk as I grab the things I need, right? The slope describes the steepness. We can take that language of how quickly it's rising or falling, and we can apply it to the equation we're using. And so we make these things visual, we make these things geometric, we make them approximate something that is physical, so that we have the words we already know to describe those physical things. Hey, Stacy. All right. So, and this is what I'm going to continue to do today. I'm going to look at different ways of taking a problem and turning it into a line, usually by finding rates of change or pieces of data. And so let's see here. I'm going to write this up on the board here. Bear with me. I am grabbing the word problems that are in the textbook. The applications on page 590. This is the physical copy of the textbook, and I'm using them as examples. They graphed for us the Celsius temperature one. It was problem number 71 in the book, but I wanted to do it as completely as if we did not know anything about it. I wanted to show the power of treating those 2 points of data, knowing when water boils and when water freezes, on the 2 different temperature scales, as a way of turning this thing into a line. I'm going to look at number 74. So I actually will write that here as a reference. And so a condo unit has been appreciating in value. So this is the rate that property goes up in value, which happens under certain market conditions. When it goes down in value, they'll use the word depreciating. Property tends to go up in value. Tends, not always. And any other property tends to devalue until it becomes collectible. Right, so you buy a new car, it goes down in value until 50 years later, it's the car everyone wanted, and as long as you have it in pristine condition, you now have a collectible value. And so it's going down in value $5,000 per year. Again, looking for these rates of change, they're going to help us because there are slopes. Now they're saying 3 years after it was purchased, it is worth $65,000. And we want to kind of find the equation of the line from this. So what we're going to do is we're going to translate these situations into things we know about lines, what we're borrowing from linear equations. So the first thing that we tend to look for is rates of change. These are our slopes. So I can say that my slope is, now I'm going to do something here that makes doing the math easier, it saves me writing a lot. This is 65,000. This is 5,000. Notice I say the word 5,000 and I say 65,000. So I'm going to say 5,000 per year. I'm going to talk in thousands. You don't usually have to write the K. You just have to make a note that it's in thousands. This happens a lot when people talk about finances or things that are in really big numbers. Sometimes instead of doing scientific notation, they'll say, hey, let's just say that we're going to talk in the thousands. And I'm going to talk in the thousands here because that means I can say, hey, my slope is 5. 5,000 per year, but I'm talking in thousands. Hope you're okay with that. We'll put it all together as we look at this. So our job is to translate this into a line or points of data so that we can make a line. Again, not because we have a physical thing, but because we have equations with lines that describe how things change for us, and we can borrow all of that language. We can borrow that language including the mathematical side. Now, I know to get a line, I have two things. I either need y equals mx plus b, or I need y minus y1 equals m times x minus x1. For this one, I need to know the starting point. For this one, I need the slope and a point. I have the slope and I have a point. Well, let's look at my variables here. Notice my money is up here. So what's going to happen is y is going to be how much money it's worth, and x is how much time in years has gone by. If I'm going to talk about this as a slope, whatever is upstairs is the y, and whatever is downstairs is the x. And so this is $5,000 per year. Our y is talking about the money, and our x is talking about the time. Well, then I do have a point here. I have when x equals 3, my house has a value of 65,000. And so that gives me a point. We'll call it 0.1. So I have a slope and I have a point. I can use this. I really want to emphasize that when we start using these ideas of lines and mapping data to points, we don't have to think sometimes. And I like that. I don't like to think. It hurts a lot. And you've seen my facial expression when I'm thinking of something. Oh, that hurts. That hurts. Wait. Let me see if I can do. I'm thinking of something. Oh, yeah, that hurts. Oh, that hurts. This conversion of data to things that make up lines means that instead of having to write little tables, try to figure out the pattern, we borrow the pattern we already know. And the pattern we already know is linear in this case. So let's finish this linearization out here. So I'm going to use point slope form. I'm going to change, I'm going to keep the variables the same. I'm going to say y minus y1, which is the 65, is equal to, well, my slope was 5, x minus x1, which is 3. I'm going to multiply these through. 5x minus 50 equals y minus 65. Sorry, I was multiplying my 5 through each point. Heard a noise in the background and pause for a second. All right, so 5x minus 50. I'm going to add 65 to both sides. and I get 5x plus 70. Oh, minus 70. Sorry. No. Add 65 to 15, and I get 50. Positive 50. So I had to grab... Sorry, the neighbor children are playing really loudly, and it sounded like they were in distress. And I'm looking out, and they're working... They're both trying to get into their play car at the same time. It was not true distress. So let me go back here and repeat this. So I multiply 5 through each term. I get 5x minus 15. I add 65 to both sides. So 15, negative 15 plus 65 is 50. And this is my equation of my appreciation. So let's break down what we have done, right? I took this thing about condos and I said, I have a rate of change. I'm going to turn that into my slope. I have my price, how much it was worth after 3 years. I'm going to turn that into a data point. This gives me an equation. And this equation is in mx plus b form. So this b tells me how much the condo was at year 0, or what its starting price was. We're going to do probably about 2-3 more examples, 3 more examples, 2-3 more examples, depending on how that time goes. But I really want to emphasize that when we're solving word problems and we have to find the equation that works for things, using the lines and rates of change, we only have 2 equations. We have y equals mx plus b, and we have y minus y1 equals m times x minus x1. We only have they're just off the top of the screen. We only really have these 2 equations. In both cases, the slope is our rate of change. So if we have a rate of change going on, we're good. Otherwise, well, no, we have the rate of change. All we need then is a data point. If we don't have the rate of change, but we have 2 data points, we can find the rate of change. And so this lets us take anything that we have 2 pieces of data from, and we'll go, okay, let's just assume it's linear. And we'll make that linear assumption, and we'll use the linear assumption to make this relationship. So instead of having to do all this juggling, remember these different equations, as long as our thing has a rate of change, we only have 2 equations to deal with. And our job then becomes mapping the rate of change and mapping the data points. Well, let's do a couple more of these, and I'll keep repeating the importance of this and how it simplifies things down. Or at least it makes us not have to worry about finding an equation. We limit ourselves to the 2. So I'm going to look at 77. Pressure underwater increases with greater depth. The pressure P on an object and the depth D below sea level are related by a linear equation. And so we're going to put that up there. So let me put this up on the blackboard here and move things around. I didn't knock anything over yet. All right. All right, let me go back to, I think I'm going to do my words in magenta. In deference to the banister. Okay. I'm going to write down the words and then I'll say them here, right? This is exactly what it was like in class. Pressure increases with greater depth. So the further underwater you get, the more water is on top of you, and that water on top of you has a rate. Pressure P on an object and the depth d below sea level are related by a linear equation. I'm going to stop here before I put the numbers in. This is telling us there is a law in the world, and the law is the relationship between the amount of pressure and the amount of water above you, the depth. And observation says this is linear. This is giving us an okay to say, hey, we're good to make this a linear equation. And a lot of laws in nature we are linear for most areas worth measuring. So the pressure at sea level is 1 atmosphere. It's a way of measuring pressure. It's the weight of the atmosphere. Whereas 33 feet below sea level the pressure is 2 atmospheres, and those are T's. That wasn't an F, that was just a little crook on my T. All right, so we want to find an equation representing pressure. So we're given that this is a linear relationship, and to be honest, a lot of times when trying to find physical laws, we start with a linear assumption and we test that assumption. So we can think of, if we wanted to graph it, very similar to what we did with the Fahrenheit and Celsius. I'll come here, I'll make my graph. And I want to know what the pressure is, given that I have a known depth. So the thing we want to find goes on the y-axis, and the thing we're inputting goes on the x-axis. And so we have this idea that as we get deeper, the pressure goes up. And what we're going to have here, let me put we're going to find we have a line similar to this, but we're going to see why as we pull it apart. Okay, so when we want to use a linear relationship, we either need to know the rate of change or we need to have 2 points. So I want to turn my problem into points of data. So if I have depth on my x-axis and pressure on my y-axis, my points of data are going to be my depth and my pressure. So to find a line, I need 2 pieces of information. I either need the slope and a point, or I need 2 points. So there is no data here. All the data kind of starts in this last part here. It says the pressure at sea level is 1 atmosphere. Well, sea level is a depth of 0. So there's 0.1. Right? The pressure at sea level is 1 atmosphere. At sea level, I am starting at no depth, right? Because the depth is related to sea level. All right. Whereas 33 feet below sea level, the pressure is 2 atmospheres. And there's my second point. P2. I'm now at a depth of 33. we have everything we need now to make an equation. In fact, because we have an x equals 0, that's also the y-intercept. So that's B. Because the y-intercept, or in this case the pressure intercept, right, or the initial pressure, when our depth is 0, our pressure is 1. And so this point here was 0, 1. So if I want to find my pressure-depth relationship, I'm going to scroll down here because I now have all this information in this form here. I need my pressure is equal to my slope times my depth plus my intercept. Notice I am changing my variables over to the things we're talking about. This is still an equation of the line. We should underneath this see the form that this is y equals mx plus b. And with it being y equals mx plus b, what's my y-axis? P for pressure. What's my x-axis? D for depth. So we found our b. Right? If our x value or depth value is 0, then our pressure value is 1. So we're going to have a plus 1 at the end here. So we're really close to being done by aligning this information to a line. I didn't mean that bad dad pun, aligning things to a line. Please forgive me. Please. I know I'm a dad, and I know I'm full of bad puns, but I don't mean them most of the time. All right, so the only thing left for our equation is to find m. And so m is the change in my y values, which in this case is pressure, over the change in depth, my x values. And so this would be P2 minus P1 over D2 minus D1. And so 33, my P2s are 2 minus 1. Right, because there's my 2 minus 1, and 33 minus 0. Or 1 over 33. And we have found an equation for our pressure with depth. Again, we've taken our data and turned them into points on the graph. By taking our data and turning them onto points on the graph, we borrow anything we have done before with geometry. We can talk about our data with that. And the things we have been focusing on are how 2 points of data make lines. And so if we have a word problem that gives us 2 points of data, we can make lines out of them. And making those lines give us the relationship between the equations. All right, let's do one more here. And again, our idea is we're going to look for 2 points of data. We're going to map those 2 points of data to a line, and that's going to help us find an equation. Trying to find, a lot of these are very physical. I did the condo, which was a price. I did the pressure and water. I was gonna want to do one that doesn't. That's a depreciation. I want to do one that doesn't have a starting point. I'm going to do 80, which is a depreciation. It's very similar to the condo problem, but it's a good example of this, and we should be getting a negative slope. So I'm going to do 80. Let me write it up here. in magenta because the banister. It's a very lucky banister. All right. A company purchased a computer workstation for $8,000. So, company purchased a computer workstation for $8,000. After 3 years, the estimated value of the workstation was $4,400. Sorry if I'm using abbreviations. The estimated value of the workstation was $4,400. And what we want to do is we want to find an equation to represent the value for age. And so we want value to be the thing we input, or the thing that outputs. We want age to be the thing we input. So we're going to think of this in terms of a line where v equals whatever our slope is times the age plus b. In general, think of the thing that you want to answer as your y value when building these formulas. So we need two pieces of data to do this. We need either 2 points or we need a slope and a point. Now, a slope is a rate of change. So in this case, it would be some amount of money per year. I don't have any slope given in the problem, but I do have how much when I bought it and how much after 3 years. So I want to turn those two places of time into points. And so my points are going to look like some value over age. So point 1, well, my age, whoops, I need to do this, did it backwards. It's x comma y, a comma v. And so point 1, well, what is my age when I buy something, right? Well, it hasn't aged yet. So that's 0. And it had a value of 8,000. I want to play the same trick I did in the condo problem. I'm going to talk in thousands. Now for point 2, well, 3 years later, it had an age of 4.4. I know, I could have kept the extra zeros. I don't know, for some reason when I do linear equations, I don't like the extra zeros on the end. Well, actually, I'll do it both ways. I'll start out doing it as written, and then I'll do it as 8,000. You're twisting my legs here. I'll rewrite it as this. Well, I need a slope. I need a rate of change. So my rate of change is my change in value over my change in age. So that's the second value, 4,400, minus the initial value, 8,000, over my age minus my initial age. This is why I'm so happy we have calculators. I could just reach them when I need them. There we go. So 4,400 minus 8,000 is minus 3,600 over 3, or minus 1,200, 1,200. I want to note something here. We should have expected to see a negative sign. The value is going down. Our slope should be negative. Okay? Our thing is getting worse. The rate of change, or worse, our thing is losing value over time. So our slope should be negative. There should be decreasing value over time. Notice I'm borrowing the words from a line and I'm applying it to how we're talking about the money here. I want that translation of words to come across. I want to why we are using the points on the line. We want to borrow that language of a line. And we are losing value over time, so we should have an equation with a negative slope. Nicely, I have here an x, or a value of 0. So this is the y-intercept of 8,000. B equals 8,000. So my equation, my value, is equal to my slope, negative $1,200 per year, times my age in years, plus 8,000. All right, I really try to end around 11:40-ish, 10 minutes early here, but we have wrapped up all the chapters on lines. The chapter on, pause, lines, not just online. I will have all the homework for the rest of the year posted up. We will have an exam on lines, and then in the final exam, I'm going to post everything so you have time to work on it. We only have one section of material to do, and it's going to be on polynomials, on things where x is squared, not linear, and what to do with it. That's going to take a little bit of time to dig through. So even though it feels like one chapter in the book, it's probably going to eat our time up towards the end. Well, at the same point, I do want to get ready for the exams. The exams coming across. So I'm going to get everything posted, and I want you guys to work on it and ask me questions as we're going through. Remember, the joy of putting things on graphs isn't that graphing is fun or great or makes pretty pictures. What it does is it lets us borrow the language that we already have. And this, like last problem, right? The value is decreasing. The slope of the line is decreasing. There are things we can say and see that we don't have to plug in numbers to figure out once we get the things done graphically. So that's the whole why we did this effort to map out the graphing plane and why we learn these things about lines. The rate of change and the slope end up being the same thing. And so when you have problems with rates of change, those are your slopes. If you don't have rates of change, you need two pieces of data to make them, because your slope formula is the difference between 0.2 and 0.1 in the y values divided by the difference between 0.2 and 0.1 in the x values. So to make things into linear equations, you need two pieces of data. You need the slope, and you need at least 1 point. All right, so fire me off email questions. I have 2 questions that I'm going to be putting examples for. Please check out the playlist on YouTube. Anytime someone asks a question that I don't cover in class, I put it up as an example. I think I might go through and do more applications out of this chapter as running examples with this high emphasis on turning them into lines. All right, if you need anything, holler. I know this was a short one, but we were really wrapping up a chapter, and I'm going to throw you some work to work on this through the week and ask questions, okay? Wow, I made it right to the end of my paper.